Hey folks, welcome to another episode of YFTT, Yugabyte Friday Tech Talks. And I have with me Franck Pachot here. We're going to be talking about Postgres joins in Yugabyte, but we still have a couple of minutes, so we'll get started in a minute or two. And thanks for taking the time, Franck.
Yeah, thanks. Hi, everybody. Yeah, we see if we are live. If people can say hello in the chat, then we know that we are live.
Yeah, I think, it's now seeming to show up at least for me. So yeah, looks live.
Yeah.
And for the folks there, I think, okay, we got a hello from Rickard. Hi, Rickard. Okay, cool. So yeah, all set on that side. Like once again, like most of the folks on the show probably know you, Franck. You've done this so many times, but it's still good to introduce yourself, and then we'll get this show on the road. Just a quick note before we start, folks. If you have any questions, please don't hesitate to ask. Both Franck and I love questions. It makes it a lot more interesting than just like some presentation. So do ask questions. You can put it right in the LinkedIn comment box. You can add it as a comment, or you can also later on join our community Slack, yugabyte.com/Slack, and you can ask questions there too. But I think without further ado, maybe Franck, kick it off. What do you have for us?
Yeah, so quickly, I'm developer advocate at Yugabyte, and we are doing a distributed SQL database that is Postgres compatible. And here we are talking about the joins. That's a question that I've seen a lot when we are talking about SQL queries and complex SQL queries on distributed SQL. People are always asking, what about the latency when you join tables, large tables from multiple rows? So we will talk about the join methods that are coming from Postgres, because we use Postgres for the query layer. But we made some optimization to get them working well in a distributed manner, better than trying to collocate tables in specific node and then limit the possibilities of join. We have join methods that can scale. So that's the idea. I will go to the slides later, but I will first want to show you what we are talking about when we are talking about joins. And I have created two tables in a cluster that I've created in multiple regions. This is Frankfurt. You see my screen, huh?
Yes.
I just have a dubbed because Zoom doesn't tell me that it's sharing, but that's fine. Yeah. So this is Frankfurt. I have London and Paris. So those have 10 or 20 millisecond latency between them. So I created a cluster where I know I have latency between the nodes, and I've created quickly two tables where I've generated 50,000 in one and 5 million of rows in the other, just to have a few rows to join. And of course, as usual, I will look at the execution plan. We use the same as Postgres with explain, analyze when we want to run a query and see the execution statistics. But we have also some additional metrics. In Postgres, you usually use buffer to see the number of logical reads from the shared buffer. Here we are doing distributed reads and writes, and this is what we want to see. And a simple join from those two tables, and without any where clause, so a join that gets some millions of rows. Of course, this is not typical from OLTP, reading millions of rows, full scan of tables with no where clause, but there is always some reporting that is made even on OLTP database. So that's a use case. And this took 6 seconds to scan both tables and get all rows and join them. So we can already say that, yeah, joins can scale. It's not a problem with millions of rows. Of course, for OLTP queries with a less number of rows, if I do the same adding a where clause where I'm getting 20 or 21 rows. This is fast. This is directly 47 milliseconds. So for the user, that's immediate. We will see how it is this fast. You can see that it looks like a Postgres execution plan. Index scan is the same as in Postgres, but we have some additional metrics with the dist, so the read request. And basically it is fast because even if I read a lot of rows, I'm doing a few read requests to the other nodes because there is some batching and we have a Yugabyte specific node in the execution plan. This is the join method that we have
So a couple of questions,
optimized.
Frank. So a couple of questions in this scenario, right? Just to explain it to our users, right? So you said that originally you had the cluster across 3 regions. Now you're firing your query, your join query into one of the regions. Now, in order for it to execute, does it fetch data from all the regions or just one region?
Here I have a table that is, let me look at it. So I deploy it with YBA where I have the old UI, but I can still, and maybe I'm not authenticated. Okay, I will look at that in a different way. I have multiple tablets in, I'm just refreshing to reconnect to show it. I have multiple tablets and I'm scanning all rows, so they come from different nodes. Yeah.
Yeah, got it. So, okay, so it fetches from multiple regions and multiple different geographic locations. And the previous one, it shows it has 12 storage requests. So that'll go to different regions and you're fetching it from all over the place, correct?
Yeah. For example, the big one was Demo 2. And so the placement is multi-region. I don't have affinitized leaders. So leaders are in all regions.
Yeah.
And you can see multiple tablets and they have the leaders in different regions. So we have definitely cross-region calls when doing that. Yeah.
Got it. Got it. Okay, great. All right. Makes a lot of sense.
And yeah, and the magic is that they are batched and we can see that it has been transformed to arrays in order to read many rows from the outer table and push the join predicate with an array.
Yep.
But let's explain a bit more the different join methods that we have in Postgres and what we have done on them to improve it when it made sense, when we had something to improve. So join methods, usually you do not choose the join method. The query planner has an optimizer that looks at the selectivity, estimates the number of rows, and then chooses the best join method. So that's the advantage of SQL databases. You don't have to think about the way you access data. The database does it. And basically, Postgres has multiple join methods. One is called nested loop, but I wanted to start by saying that they are all nested loops, which means that it joins between 2 tables. Even if you join 3 tables, it will join 2, and then the result will be joined to a third one. So between 2 tables, there is the outer table and the inner table, or sometimes called the left table or a right table. In the execution plan, the outer is on the top. And basically, there is a loop on the outer to get the rows you want from there. And there is a loop in the inner one to get the rows that match them. So all are loops. The difference is that with the one that is called nested loop, the join condition is pushed down to the inner table. I can show it here, for example. We can see that I joined on n, the column n from demo 1 and column m from demo 2 must be equal. And we can see that this is an index condition here because it is batched. We see an array, but it is in the index condition. The join condition here has been pushed down. So that's really useful when you have
one quick interrupt, Frank. So Mladen asks if YB has parallelism. So in that context, so when you push down the join, can it go in parallel, etc.? So maybe we just take that quick interrupt and then continue. Yeah,
that's a really good question. So there are two things. We have the storage that is distributed, and we have some parallelism there. When we, for example, when we scan a big table and we know that we will retrieve a few rows from many tablets, we can send those read requests in parallel. So that's the Yugabyte distributed parallelism. And on top of it, Postgres has parallel query, where the query planner decides to split the scans, for example, and run them in parallel. So the backend is a coordinator and can process a chunk of it, and then other workers work on that. So that's Postgres. Today, currently in the current version, we don't have that in Yugabyte, but this is work in progress. We will have that. Mostly because even if we are optimized for OLTP, there are some reporting, there are some analytics that will benefit from that. The main advantage will be that if we read a lot of rows that we have to bring back to the SQL layer, we don't want to distribute all those scans and finally have only one process that will have to, let's say, aggregate all of them. So with parallel query, that will come. So we have those two levels. Currently, it's only one process on the SQL layer that will come in future versions. So yeah, when with nested loop, the advantage is that the join condition is pushed down, which is good when you have a large table, but the right index for the join condition. And then you can, in the inner loop, you can fetch the rows that match quickly because you have a structure and index that access to it. The other join methods do not push down the join condition. So what they do, they read all rows from both tables, maybe not all rows because there are some conditions on the table, but the join is done after that. So with the other methods, even the inner table is read once, and then the condition is applied on the results. And there are different methods because when the rows are read from the inner table, Postgres builds a structure to get them faster. So basically, if you have an index, you do a nested loop and you use the index that is hashed, sorted to get the rows. If you don't, you get all rows, you put them in a temporary table that is hashed or sorted, and where you have fast access on them. And the different join methods are the way they are hashed or sorted. If it's a hash join, then the inner table will become a hash table. If it's a merge join, the two sources are sorted, and then it's easy to join them just by scanning them in the right order. And there is also the possibility where a nested loop cannot push down the join condition, and then we'll still do a nested loop, getting the rows in the buffer, not hashed, not sorted, but if it's small and if there are not too many loops, it's still better than accessing the table. So basically, the other methods are just reading the rows, and then the optimization that we will see for that go in two ways. First, those join methods that gather a lot of rows to join them later, you want to gather those rows fast. And for the nested loop that will get to the inner table multiple times, you want also to batch something there. So that's the idea of those join methods. The query planner decides what to use depending on the size. For example, if you have 3 rows coming from the outer table and fast access with an index to the inner one, you just get those 3 rows and that's fast. If you join a very large table with a small or medium one, then the small or medium, you take it, you put it in a hash table, it fits in memory, in the work memory of Postgres, and then the join is fast. If you have rows that are already sorted, for example, because they come from an index scan, then merge join can be easy because merge join doesn't have to sort it in addition to that. Also, if you have an order by that wants the results sorted, maybe it's faster to sort them before and join them later. So those conditions are decided by the query planner. Currently in Yugabyte, the cost-based optimizer is not enabled by default, but that will come soon. The idea is that we will use the same optimizer as Postgres, but with additional consideration for the fact that it may come from different nodes. So we are implementing the cost-based optimizer using statistics to get the selectivity, but also with a cost model that fits the distributed database.
So net effect, right? As a user, when I think about this whole thing, I don't have to worry about how the data's execution of the query happens. The cost-based optimizer will match how Postgres works at the highest level and optimize it and fit it for Yugabyte's execution. And what I will get is very similar to Postgres type execution, semantics, performance, etc. over time. And like I don't have to think about the detail. That's what it'll come to, right? And it'll pick, say, a batch nested loop join at the right time or whatever the query plan is at the right time.
Yeah. And of course, not everything is perfect. Sometimes the queries are so complex and the data is skewed that it's difficult for the optimizer to estimate the cost exactly. So there are two things there. The first one is that even if the query planner doesn't choose the best join methods, the idea is that all join methods are okay. Maybe one is better than the other, but all are okay. So if the query planner didn't pick the best of the best, then it's still okay. And if there are a few special queries that are so difficult to optimize for the query planner, we also have by default PG in plan where we can fix something or maybe fix it before looking at exactly at what is missing, maybe some statistics. So with the join methods that we have seen for Postgres, what did we do in Yugabyte and why? We are a distributed SQL database. We allow tables to be distributed on all nodes of the cluster. Of course, we can restrict that if we want to geo-partition and put some data in specific regions, for example, but by default, data can be everywhere. We do not constrain specific privilege join hierarchy. Everything can be distributed. So if we do nothing, if we just use the nested loop as it comes, and if we just fetch rows like Postgres does, Postgres get them row by row because Postgres read them. Postgres runs on a single node where it has the shared buffers in memory, and you can read from memory with random reads without penalty. But for us, we cannot share the shared memory between multiple nodes. There are network calls. So if we do it row by row, the problem is that we will add 1 millisecond or more for each row. And of course, that doesn't scale. So the idea is that we want the same performance as Postgres, which can read from the shared buffer with 1 microsecond per row. And we want the same performance even if we have 1 millisecond between the nodes. And to do that, we have two solutions. One is when there is many small tables that are joined, we can collocate them in one node because you don't want to distribute, let's say, 50 tables that are 100 or 1000 rows. You don't want them to distribute. So that's one thing for the small table. But the big tables, you want to distribute them. You want to have rows in multiple tablets, in multiple nodes. And then to solve that, we batch everything. When we get rows from another node, we don't want to get them row by row, even if Postgres by default does that. We want to batch the read and write requests. And basically, if we have 1 millisecond latency to get 1,000 of rows, we reach the same performance as Postgres that can get 1 microsecond per row, because you divide the latency per the rows, and this is how we get the similar response time as Postgres, even if there is some latency. The idea is that if you join 3 tables, it is okay to have 3 milliseconds for the 3 tables, but that should not be multiplied by the number of rows. Of course, if you read, if the batch is 1,000 of rows, you may have multiple read requests, but you already have thousands of rows with that. So 2 things are batched. One is not specific to the joins and is there by default. I mentioned the parameter, but you don't have to change it. It's there by default. It's the fetch size when we read from a table, from a tablet. So for example, if we do a hash join, we get rows from the 2 tables to join them later. To get those rows, we want to get them 1,000 per 1,000, and that's this parameter. And for the nested loop, you get the rows from the outer table with this fetch size. But if you use the nested loop from Postgres, you will get, for example, you get 1,000 of rows from the outer table. If you do 1,000 of loops, then you add the latency. So the loops themselves has to be batched. And sorry, I have a typo. The parameter, better to show it here. The parameter is the batch nested loop size. Let me show you those ones. So first, I reconnect to set the default, the config. All the specific Yugabyte parameters start with YB, and ones related with the batching of the nested loops are YB BNL for batch nested loop, and the default batch size here I'm using 221, so the version that will be there next month. Select start from version. If you use the current versions, the default is still 1, and you can set it to 124, which probably fits all needs. And also in 221, we have a preference for batch nested loops, so it will be batched when it can. So 221, those parameters will be the default. The cost-based optimizer is not yet the default. You can set it, but even if it's not set, there is a preference for the batched nested loop. And before seeing what is next, let me show more example of about those. I also mentioned the fetch limit. So we have by default batching of 1024 rows, and we also introduce a parameter to choose this limit with the size, because there are applications with very small rows and there are applications with large rows. So better to have control on the number of rows and the number and the size of the batch that is read of the read request. So here I'm in 221 with the default. And if I just join as I did, we have seen that by default, we have this YB batch nested loop. And the difference is that if, let me first force the Postgres nested loop. I do that with an int, the nested loop int, because we have PG in plan. This one will force the Postgres nested loop. So the code that comes from Postgres without anything changed by Yugabyte. And this one, of course, I have 20 rows, so it's still fast, but it's not the same. It's 200 milliseconds instead of 45 here. But this one, when it retrieves 20 rows from the outer table, it will loop 20 times to fetch the rows from the inner table where the condition is pushed. So basically, when we do that, we do 20 read requests. In the Postgres execution plans, when you have a loop, you have the number of loops there, and all other numbers are per loop. So this is request per loop. I can enable the summary maybe to show the total. It's just taking all the screen. The summary is 21 read requests, 1 to get the 20 rows from the outer table, and 20 loops. So that's the nested loop, and that's something for 20 rows, still okay. For 1,000 of rows can be very long, and this is why without the int, we have the batch nested loop, where we have only one loop, but with all the 20 values sent there, with an also pushed down, but with an array coming from that. So we don't show all the values of the arrays because it takes space on the screen, but basically it can send up to 124, the batch size, in an array, and can be complex. It can be, even if we have conditions on multiple columns, as long as it can be pushed down, it is pushed down. So that's the batch nested loop. Of course, the other ones, the other join methods are still available. I will use ints to show them, just to explain and show the difference in the execution plan. Let me just take one where I have an int with all, and if I ask for hash join, for example. So this one will take much longer because it will have to read all rows. So from demo 1, it will read the 20 rows, but it will read all rows from demo 2 and fetch all them at the same time. And if I want it faster, so of course I have millions of rows, so that's probably too much. If I want to do that faster, maybe I can change the fetch. The one that I said the default is okay, but with million rows. Okay, this one should probably take just a few seconds, but looking at the time, I will switch quickly to the, so it was there. Just wanted to explain that if you have a doubt about the performance of a join, always look at the execution plan. Here, I can see exactly where the time is spent. The time is not spent to get the 20 rows from demo 1, because this takes 18 seconds. The time is spent in scanning the millions of rows, and this is done in multiple read requests there, the fetch size, and then it is joined. So you can really see that here 4 seconds was taking by the getting the million rows, and then the join on top of it was 2 additional seconds. So always look at the execution plan, and here I used dist to get the number of read requests, and you can have also more information with a debug to get more information. So always good to look at the execution plan to understand the performance, and you can also do the math. If you know that you have 10 millisecond latency and you are doing 10 read requests, you expect 100 milliseconds. There is no magic. You cannot do less than that. And if you do more, that's probably because it's not working in the right way.
Yeah. And one question from Laden again. What about the costs of parsing? Are SQL statements all parsed and optimized on the receiving node, or will the parse be distributed across all nodes?
For the moment, the parsing, so the parsing and the planning is done like Postgres, exactly like Postgres. So the backend where we are connected parses it. it's still distributed because another connection will be connected to another node and then will pass on another node. So it's still distributed, but for your own session, you have a dedicated backend. That will change also with the connection manager. When I say dedicated backend, if we have many connections, we have a connection manager that can pull that, and then it will be dedicated only for the duration of your of the parsing. But that's done exactly the same as Postgres. With prepared statements, you can also parse it once and execute many times. Basically, it's the same. Even if we have changed something in the query planner to have a cost model that fits the distributed one, and even if we added a join method, it's not something that takes more time in parsing than in Postgres. We didn't add some big transformations or anything.
And given it's a OLTP transactional database, operational database, the parsing overheads usually are not as much as the execution overheads, right? So it's we don't do super unlike an analytics or a warehousing database where parsing can be a much more.
Yeah, and also something in Postgres, there is no shared cursors between sessions, like, for example, commercial databases have. And for us, it's also good because we don't want a shared memory that can be accessed by multiple nodes. So the Postgres model really fits the distributed database for this one. Each one will be parsed, and if there is too much overhead in parsing versus executing, then just use prepared statement and they stay prepared. Yeah. I just wanted to mention, if users were using the feature in preview, the batch nested loop, before 2.21, they had to set the batch size because it was 1 by default. And if in addition to that, they used the nested loop int to force a nested loop, so the parameter to make it batched and the int to make it a nested loop, this will change in 2.21 because we really consider this as a new join method, and then we have a new int. So as I did in the demo, you can use the Postgres, so the pgin plan int nest loop to force the non-batch one. And if you want int to force the batch one, you have it, and we have also parameters for that. So just mentioning that this is something that that has changed when we make it default. So in 2.21, you don't have to worry about it. It will be all default and chosen. And what we have seen, it was in preview before, and we have many customers who used it. For the moment, for me, it was really the magic solution for many complex queries that come from application made on Postgres. With batch nested loop, we can really take complex query and then have good latency on YugabyteDB with that, and without ints. Yeah. Okay. In the slides, I just mentioned the GitHub commits about that. And yeah, something also important to mention, I will not demo it, but the last addition we did on it was to preserve order, because when you batch, the final order may be different, but preserving order is very interesting when, for example, when you do pagination, you read, you have an index on the join column, and you also want to order on this join column and have a limit, just fetch the 10 first rows. You don't want to read all the rows, sort them just to get 10 ones. So if the order is preserved, the order that comes from the index is preserved after the join. And this has been also added and will be there in 2.21.
Awesome. Fantastic. Thanks, Frank. I think Mladen was commenting that, yes, shared pool is an incessant source of fun in Oracle RDBMS. So.
Yeah.
All right.
It's different times. Today, the CPU, the time taken by the CPU to parse queries, it's not as important as it was before. So yeah.
Yeah, that's right. Yeah, that's right. And especially in a distributed, it's far more the plan and the execution of the plan far more important. So yeah. Totally agree. Awesome. All right. Thank you, Frank. Thank you, everybody. It was really interesting. I hope you guys learned something. I learned a lot, so it was nice. And as always, Frank is excellent in the way he delivered it. So thanks a lot, Frank. Really appreciate it.
Thank you.
Yeah, and once again, folks, you don't need to stop asking questions. Please continue to post questions here. You can join us on our community Slack. Frank has the link up there, yugabyte.com/Slack. And, do follow us on GitHub and, join us in a couple of weeks, once again, for another episode of YFTT, which is a talk by engineers for engineers. But until then, thank you. And Happy New Year, everybody. Should have started with that.